Alrighty. Good morning, everybody. Welcome back to Calc 2 after a long weekend. Apologies for missing class on Friday. Woke up Friday morning in no fit state to teach. A little bit of a rough weekend, but I'm feeling a lot better now. Thank you to those of you who reached out to me with warm wishes. Plan for today is we're going to continue our discussion of inverse trig functions from last Wednesday's class. We kind of started getting into some review of what inverse functions are. Today we're going to be focusing on looking at various inverse trig functions, how do we evaluate them, and also how do we differentiate them. I've got my usual office hours over the next few days, 11 to noon and 1 to 2. As far as homework goes, I was getting some requests / homework questions from a bunch of you over the weekend, so I decided to, I'm not assigning any new homeworks today. Instead, what I'm doing is I'm pushing back a couple of homeworks. Homework 6 is now going to be due on Wednesday. That was the one that was originally due last Friday. And homework 7, which was originally due for today, I believe, is going to be due on Friday. Give you all the opportunity to have a little bit of extra time to work on those. Come ask me if you have any questions. Dr. Gersel, how are we going to make up the class that we missed? That's the one freebie. Any future classes that get canceled due to me being sick or out or whatever, I will have some way of making up. But yeah. Any questions or comments before we get started for today? What type of math is most commonly discussed between seabirds? Type of math that's most commonly discussed between seabirds is intergull calculus. Alright, and with that, let's hit the ground running. So last week, by the way, apparently Super Smash Bros. Tournament, Saturday, March 4th, 2 to 5 p.m., Student Union TV Lounge. I grew up on Super Smash Bros. I think I'm still the faculty advisor to this club, so if y'all have any interest in that, stop by. But also, if you do, let me know. I might show up myself then. So last time we talked about inverse functions in general and started talking about the question of why is it difficult to try and invert a function like sine of x. And the idea behind taking an inverse of a function is the inverse of a function f of x, which we usually denote f, and it almost looks like an exponent of -1. Do not be deceived. This is not an exponent. It just kind of looks like one. F inverse of x, where the relationship is if f of a is equal to b, then f inverse of b should be equal to a. So in essence, we said that an inverse function basically just flips what are the x coordinates, the inputs, and what are the y coordinates, the outputs of your function. And we ran into a problem. Last time with trying to invert sine of x. And our problem was we looked and found several different angles that the sine function maps to 0. So in particular, we said sine of 0 is equal to 0. Sine of, say, pi is equal to 0. Sine of 2 pi is equal to 0, and so on. In fact, sine of any integer multiple of pi will always map to 0. So why did we say this was a problem in trying to find an inverse function for sine of x? I think
it wouldn't be a proper function because there would be points, like multiple points for one x, there would be like multiple y coordinates.
Yeah. If we tried to invert using kind of this formula up here, what we would get is that if we swap the x and y coordinates here, swap the input and output, well, in this case it wouldn't really change anything. We would get that inverse sine of 0 is 0. If we swap our input and output here, well, actually need to swap. Well, if sine of pi is equal to 0, it would logically make sense we would want for inverse sine of 0 to be equal to pi. And similarly, since sine of 2 pi is 0, in order to follow this formula up here, normally we would want something like inverse sine of 0 is equal to 2 pi. And this can't happen, we don't want this to happen, because then inverse sine wouldn't be a function. Part of being a function is that one input maps to one output. So we can't have inverse sine of 0 be equal to several different values. Unless your name is James and you want to map inverse sine of 0 to the entire set of real numbers that when you plug them into the sine function you get 0, which instead of giving you a function from r to r, gives you a function from r to the power set of r. But we're not going to be doing that in this class. Sorry to disappoint. Instead, here's what our idea is. And I'm going to be on the second page of the Standard 5 packet. What we're going to do is we're going to define inverse sine of x in a way that kind of avoids this mess. And that we're going to say that y equals inverse sine of x is going to be the unique angle in the interval from negative pi over 2 to positive pi over 2 that satisfies the condition that sine of y is equal to x. So in other words, we're saying inverse sine of x is not just going to be any old angle y that maps the sine function would normally map to x. Instead, it's going to say pick the angle that's in the interval from negative pi over 2 to pi over 2 that has sine of y equals x, and then inverse sine of x is defined to be that value of y specifically. So with that in mind, Rhoda, what would we say inverse sine of 0 is in this case? In order to fit with that definition. In other words, which angle between negative pi over 2 and pi over 2 satisfies sine of that angle is equal to 0? Nope, sine of pi over 2 is actually 1.
Oh.
Cosine pi over 2 is 0.
Wait, can you ask the question one more time?
Sure. So with this definition in mind, what would we say that inverse sine of 0 should be equal to?
Oh, 1.
So you're saying then that 1 is an angle between negative pi over 2 and pi over 2, and sine of 1 is equal to 0?
Yes.
I don't think sine of 1 is a particularly nice number. James?
Should be 0.
Yeah, I think so. I think, for instance, we would say it should be 0. Because there's lots of different angles, like 0, pi, 2 pi, etc. Lots of different angles that if we plug them into the sine function, y equals sine of x, will map to an output of 0. But there's only one of these angles, one of these infinitely many angles that map to 0 when you plug them into the sine function, that would satisfy that that angle is between negative pi over 2 and positive pi over 2, and that angle is 0 exactly. So we can similarly define formulas for inverse trig functions for our other 5 trig functions, cosine, tangent, etc. we could say that y equals inverse cosine of x is going to be the unique angle in the interval from 0 to pi, satisfying that cosine of y is equal to x. So, question. Why do we have a different interval for inverse cosine than we do for inverse sine? For inverse sine, we say pick the angle in negative pi over 2 comma pi over 2 that does what we want it to do. For inverse cosine, we're saying, no, don't pick the one between negative pi over 2 and pi over 2 necessarily. We're picking the angle between 0 and pi that does what we would like it to do. So why the difference? Bethany?
Because if you look at the unit circle, the sign, like all of its points that we want to like take into consideration are all of its like the lengths of pi, which is like the distance upward, will be on like the interval of like pi halves to negative pi halves, whereas on like cosine, all of its like lengths and on the horizontal axis will be from 0 to pi.
Yeah, that's exactly right. So if we look at the unit circle, in other words, let me find the right page. I put one at the back of your packet. If we look at the unit circle, and we look at sine of x, keeping in mind that sine of x means you go to x radians and then you take the y coordinate of that point on the unit circle. The sine function from negative pi over 2 at the bottom of the unit circle up to positive pi over 2 at the top of the unit circle, sine of x never repeats itself. And we go from values of x where if you plug them into the sine function at negative pi over 2, you would have y equals negative 1, up to x equals positive pi over 2, you would have sine values up in this first quadrant here, where sine of x is positive. So from negative pi over 2 to positive pi over 2, sine of x never repeats itself. But if you look at the same interval from negative pi over 2 to positive pi over 2, cosine of x is going to repeat itself. So for instance, I can find two different values of x in the interval from negative pi over 2 to positive pi over 2 that will make cosine of x come out to the same thing. So as a quick example, Jonah, what would we say is going to be cosine of negative pi over 4?
That'd be the same as 7, or it'd be radical 2 over 2.
Yeah. Because if we start at 1 comma 0 and move pi over 4 radians, or 45 degrees, downwards in a clockwise manner, we're going to get to a point where the x coordinate is positive root 2 over 2. Katie, what other angle between negative pi over 2 and pi over 2 is going to have a cosine of root 2 over 2, other than negative pi over 4?
Would it be 7 pi over 4, but would that be then just negative pi over 4?
Well, negative pi over 4 is certainly one angle, but what other angle in this interval, so along kind of the right half of the unit circle, is going to have a cosine of root 2 over 2?
Other angle? Wouldn't it just be the reflection of it across? Or am I totally lost?
No, you're on the right track. So what would that be? Wouldn't be negative pi over 4.
Maybe cos pi.
Yeah, exactly. So we can see from this that cosine of x repeats itself over the interval from negative pi over 2 to pi over 2, because you can find two different angles between negative pi over 2 and positive pi over 2 that are going to map to the same thing. So if we tried to define inverse cosine as pick an angle between negative pi over 2 and pi over 2 that cosine of y is equal to x, we'd be out of luck, because we'd be saying things like, oh, inverse cosine of root 2 over 2 is equal to both negative pi over 4 and positive pi over 4 as well, which we would rather not have happen. Nora, what other angle other than positive pi over 4 and negative pi over 4 between 0 and pi satisfies cosine of that angle is equal to root 2 over 2?
3/4 pi?
Nope. 3/4 pi maps to negative root 2 over 2. Is there another angle in there?
No.
Nope, there isn't one. Sorry. Quick question there. But the idea is cosine of x repeats itself over the interval from negative pi over 2 to pi over 2. You could have cosine will map to positive x values from negative pi over 2 to pi over to 0, and positive x values from 0 to pi over 2. But cosine of x will not repeat itself over the interval from 0 to pi. Because from 0 to pi over 2, we're getting, cosine will give us positive values, but from pi over 2 to pi, cosine of x will give us negative outputs. And so it's not going to be repeating itself from 0 to pi like it does from negative pi over 2 to pi over 2. Any questions or comments related to that? So, flip back to my packet. Flip back to the packet here. We can define formulas for all of our other inverse trig functions in the same way. We can say that inverse tangent of x is going to be the unique angle in negative pi over 2 to pi over 2, such that tangent of y is equal to x. We could say that inverse cosecant of x is going to be the unique angle in negative pi over 2 to pi over 2, not 0, such that cosecant of y is equal to x. Y equals inverse secant of x is going to be the unique angle in the interval from 0 to pi, not including pi over 2, such that secant of y is equal to x. And finally, we can define inverse cotangent of x is going to be the unique angle in the interval from 0 to pi, such that cotangent of y is equal to x. And so all of these functions are basically being defined in the same way. We're taking the original trig function and we're just swapping its x and y coordinates. But for each of these different inverse trig functions, we need to pick some interval where that trig function doesn't repeat itself. It's not taking on the same values more than once. Any questions or comments about how we define each of these trig functions? And a lot of dead-eyed looks this morning. Is it because it's 7:45, because we're talking about trig functions, because we're talking about inverse trig functions, or all of the above?
Some in columns A, B.
Some in columns A, B, and C, or the fact that it's a Monday. James?
Oh yeah, so when we have these on like a quiz, will we have a sheet that shows us like which interval we should use?
Nope.
Okay.
That being said, what I will give you on a quiz is a copy of the unit circle.
Okay.
And if I were to ask you, for instance, something like, find inverse cosine of root 3 over 2, for instance, these are the two I really want you to know,
Okay.
is inverse sine, inverse cosine.
Okay.
These are going to be somewhat important, particularly inverse tangent and inverse secant, for reasons we'll talk about later. But these are the two that I would want you to remember the interval for on the quiz.
Okay. And if we're in doubt, could we just write on the top like this is the interval we're assuming?
Oh, if you don't remember the one I want you to work with, just make up your own interval over which it would work.
Yeah.
Fine. As I say, how much freedom do I want you to differ? But it better be an interval that works.
Yeah.
So like for inverse cosine, for instance, don't be giving me negative pi over 2 to pi over 2, because we just talked about why that wouldn't work.
Yeah.
But you could use, for instance, for inverse cosine, you could use like pi to 2 pi instead, and that would work out. 'Cause
Okay.
pi to 2 pi, bottom half the unit circle, inverse cosine wouldn't repeat itself, just like it doesn't repeat itself from 0 to pi. So let's look at a couple examples of actually putting these into practice. Just evaluating some inverse trig stuff. Let's not right there. Lauren will do her stuff. Sorry, Dr. Murphy. So, as an example, what if we wanted to evaluate inverse sine of 1? Well, I would say inverse sine of 1 is going to be the angle theta where sine of theta has to be equal to 1 and theta has to be in the interval from negative pi over 2 to positive pi over 2. So with that in mind, Sarah, what angle between negative pi over 2 and positive pi over 2 will give you a sine of 1?
Sorry, I don't have the inner circle from last week.
You can't have that. Does anyone still need a copy of the standard 5 packet? Okay, this is So, sorry, I forgot you were out last Wednesday when I passed this out.
Is there another one?
I suppose there is. So if you flip to the back page, Sarah, what angle on the unit circle, if you plug it into the sine function, you would get an output of 1 between negative pi over 2 and positive pi over 2? Yeah. We're going to get theta has to be equal to positive pi over 2. one at the very end of this interval. Pi over 2 is certainly in between negative pi over 2 and itself. And if you go to pi over 2 on the unit circle, you go to the tip top of the unit circle, that's going to be an angle that sine of pi over 2 is equal to 1. Therefore, we're going to say that inverse sine of 1 is equal to pi over 2. How about, let's do an inverse cosine example. How about inverse cosine of negative root 2 over positive 2? So for this one, we want to find an angle theta where we need two conditions that theta satisfies. Joy, what would be one of those two conditions? Yeah, we need that cosine of theta is equal to negative root 2 over 2 to satisfy the inverse function swapping x and y coordinates. What other condition do we need for theta to satisfy? Sorry?
It needs to be between 0 and pi.
Yeah, we also need that theta has to be between 0 and pi. So what angle between 0 and pi is going to have a cosine of negative root 2 over 2? Nolan?
3 pi over 4.
3 pi over 4? Let's take a look. Gosh. Feel free to tear out your unit circle if you don't want to have to keep flipping around in your pack about it. Take your own advice. 3 pi over 4 is certainly between 0 and pi. And if we look at the x-coordinate of our point at 3 pi over 4, we get negative root 2 over 2. And I think it checks out. So we're going to get theta is equal to 3 pi over 4. With the idea being there's infinitely many values of theta that have a cosine of negative root 2 over 2. 5 pi over 4 would be another theta that has the same cosine, but there's only one value of theta between 0 and pi that'll satisfy this condition, and that's theta equals 3 pi over 4 specifically. Any questions or comments about how you would use these definitions to actually evaluate your trig functions? Yeah, Bethany.
I was just wondering about the inverse cotangent of x because I'm wondering why is it the interval 0 to pi? Like why isn't it negative pi halves to pi halves?
Oh, good question. So for that one, why are we not including from negative pi halves to pi halves? Basically, it's because we want to have an interval that avoids 0. Because here's the thing. How would you evaluate cotangent of 0? Cotangent, by definition, is cosine of 0 over sine of 0. What are cosine and sine of 0, respectively?
Cosine of 0 is 1, sine of 0 is 0.
And what does 1 over 0 come out to? It comes out to sadness is what it comes out to. So 0 is in the interval from negative pi over 2 to pi over 2. That's why we typically don't choose negative pi over 2 to pi over 2 as our interval for inverse cotangent. But 0 isn't going to be in the interval from 0 to pi, assuming you make that an open interval, so that would avoid that issue. By the way, just a quick mention, why for inverse cosecant and inverse secant, we have like an angle in the middle of our interval where we say don't use this one. That's just because secant of pi over 2 is undefined because you'd be taking 1 over cosine of pi over 2, 1 over cosine of pi over 2 is 1 over 0 is sadness, and similarly here, cosecant of 0 is undefined because you'd be taking 1 over sine of 0, which is 1 over 0 equals that. Gabe?
I was wondering, what do the inverse trig functions look like graphed out?
Oh, good question. Well, we can use our trick that we talked about last week, where we basically take a function, reflect over the line y equals x. So for sine of x, if we only graphed out sine of x from negative pi over 2 to pi over 2, we'd be getting a function that looks something like what? Like that. That's our y equals sine of x. So if we wanted to take that function and then reflect across the line y equals x. Oh yeah, let me color chalk in here. What we would get for, say, inverse sine of x would be something like that looks like that. This graph may not be drawn to perfectly to scale. But the idea is, if you want to kind of see what the graph of this of the inverse trig functions look like, what you can do is you can take the corresponding trig function over the interval that you're given, graph out that trig function, and then sort of do that, take the mirror image over the line y equals x to see what happens when you swap your x and y. Swap your x and y coordinates. That sound good? Just like how last semester we were able to find a graph of the natural log function by graphing out e to the x first and then doing that same sort of reflection. All right, Dr. Gerstel, I've seen all of this in high school, all this inverse trig function stuff. It was the bane of my existence. Why are we talking about them again? Well, we're talking about them again because we're going to use them to do some derivatives and integrals. Specifically, our goal is we're going to be evaluating some integrals using inverse trig functions, including that integral from last Wednesday that's going to tell us what the area of a circle is kind of our ultimate goal in this packet. So let's look at some derivatives to start out with. I would like to differentiate inverse sine of x. So how do we do that? Well, from the get-go, we could try and use the limit definition of the derivative, which if you tried to do that would make you cry, would make me cry. So we're going to see if we can get around that somehow. So we don't know how to differentiate inverse sine of x. What function that looks a lot like inverse sine do we know how to differentiate?
Sine.
Yeah, sine of x is something we know how to differentiate. Derivative of sine of x is cosine of x. Those of you who are in Calc 1 with me, we actually proved that last semester using the limit definition and some trig formulas. So, what we're going to do is we're going to turn this around and say, well, if y is sine of x, that's the same as saying sine of y is equal to x. And what we're going to do is we're going to differentiate both sides of this equation with respect to x. Don't worry, I'll do the hard one for you. So how do we differentiate sine of y with respect to x? Aiden?
Well, since we know y is just a function of x, so we have a function set of functions, so we'll need chain rule.
Mhm.
And so I think we'd be able to say that, I think y prime times cosine of y.
So we're going to get, when we differentiate sine of y, we're going to get cosine of y. But we also need to remember to multiply by the derivative of the inside piece, according to the chain rule, where the derivative of y with respect to x is just going to be a dy dx if you're a Leibniz person, or a y prime if you're a Newton person. And if we want to get then dy dx by itself, we can divide both sides by cosine of y and get dy dx is going to be 1 over cosine of y. If y is originally a function in terms of x, y equals inverse sine of x, it'd be nice if our derivative, if we could somehow write that out as just being an expression that's written in terms of x. So how could we rewrite our dy dx formula so that it only has x's in it instead of y's in it? Becky?
Did you substitute the original function into?
Yeah, we know y is equal to inverse sine of x, so cosine of that same y should then be 1 over cosine of inverse sine of x. And boom, we have ourselves a derivative formula. dy dx is equal to 1 over cosine of inverse sine of that same x. Aiden, quick question. When you differentiated sine of y up here to get cosine of y times dy dx, or I think as you stated, cosine of y times y prime, what did we call that type of differentiation?
Explicit differentiation.
Yeah, so if you remember from Calc 1, this was called implicit differentiation, where we have a function of x and y, not just y as an expression in terms of x that we're differentiating. In fact, for those of you who had Calc 1 with me, that would have been Standard 8 last semester. Nathan, does this look like a nice formula to you? 1 over cosine of inverse sine of x.
Depends on what we're gonna have to do with it.
Depends on what we're going to have to do with it. To me, that looks ugly. We have an inverse trig function inside of a different trig function altogether. Maybe not altogether, but. I see something like that, and I think ugh. And I want to ask the question, how can we simplify this? And we're going to have a sneaky technique that we are going to use in order to simplify 1 over cosine of inverse sine of x. And the way we're going to do it is using some good old-fashioned right triangle trigonometry. Specifically, be doing some good old-fashioned SOHCAHTOA. Has everyone seen SOHCAHTOA before? Or at least remember having heard that at some point in your mathematical lives? So the idea behind SOHCAHTOA is if we have a right triangle where, let's say this angle is theta, then the SO part of SOHCAHTOA says that sine of theta should be equal to the length of the opposite side of the right triangle divided by the length of the hypotenuse, where SOH gives you the SO part of SOHCAHTOA. Similarly, we could get the CAH part of SOHCAHTOA, where the CAH part, CAH, cosine, is going to be equal to the length of the adjacent side over the length of the hypotenuse. CAH, CAH in SOHCAHTOA. What would tangent of theta give us? Anna?
Opposite over adjacent.
Yeah, opposite, the O over the A, opposite over adjacent. And if you wanted to, you could find cosecant, secant, or cotangent by just taking reciprocals of any of these. So what I'm going to do is I'm going to do some good old-fashioned SOHCAHTOA to see if we can simplify this mess. Specifically, I want to find out what is cosine of inverse sine of x going to be equal to. And what I'm going to do is I'm going to let theta be equal to inverse sine of x. And do a little substitution in our right triangle here. So if theta is equal to inverse sine of x, another way of saying that is to say that the sine of theta should be equal to x. Or in other words, equal to x divided by 1. So using the SO part of SOHCAHTOA, the fact that if sine of theta should be equal to the length of the opposite side of the triangle to theta over the length of the hypotenuse, we could say if sine of theta is equal to x over 1, we can represent that visually by saying opposite side has length x, hypotenuse of the right triangle, hypotenuse again, just longest side, is going to have a length of 1. And now, what we're going to do with that is we want to find a nicer formula for cosine of inverse sine of x. Well, cosine of inverse sine of x is just going to be the same as cosine of theta in this right triangle, which using some is going to give us, okay, I promise I won't keep doing that. I think you all need some bird calls to wake you up or something. We need to take the length of the adjacent side of this right triangle divided by the length of the hypotenuse. So, what is the length of the adjacent side of this right triangle? So, we have a hypotenuse of 1. If the opposite side to theta has length x, What's going to be the length of this last remaining side? Or how could we find the length of this last remaining side? James?
The Pythagorean theorem.
Pythagorean theorem. Yeah, so we could say, I need a variable name.
A.
A. Whatever the last side of our right triangle is, we know that, more scratch space. We know that a squared plus x squared should be equal to 1 squared. And then if we want to solve for a, what we would get in our right triangle is that a squared is equal to 1 squared minus x squared, which is just the same as 1 minus x squared.
I was just gonna say, can't you just use a trig identity and then use sub to like get what it is?
What the a is?
What the derivative is.
I mean, explain. How would you use the trig identity in a u sub?
But if you just did, if you had u1 over cosine of sine of inverse, that's like what you started with, and then you just use the sine squared plus cosine squared equals 1, and then you did 1 minus square root of that, and then you subbed the cosine of inverse of cosine, which would be x, which would be 1, which would be 1 minus e squared, square root 1 over that.
Essentially, that's doing the same. You could do that, and essentially that's the same thing really as what we're doing here. I like doing it this way because or at least stating it this way because it kind of relates it back to these high school geometry ideas of SOHCAHTOA and right triangles. But essentially, Kate, what you just described is doing the same thing. So if a squared is 1 minus x squared, that's going to give us that a is the square root of 1 minus x squared. Similar to how you could write cosine of as just being square root of 1 minus sine squared x. But yeah, you could. And so then, cool, that tells us what our a is. Our a is going to be square root of 1 minus x squared. So with that in mind, what's cosine of theta going to be in this right triangle? Devin, you want to give this one a go? If we look at this right triangle, we want to take the adjacent side, which is this one we just found, divided by the length of the hypotenuse.
So that's just gonna be square root of 1 minus x squared over 1, which is just square root of 1 minus x squared.
You got it. Turns out, cosine of inverse sine of x is just going to simplify down to square root of 1 minus x squared. So when all is said and done, we come back over here, and we want to find what's our formula for the derivative of inverse sine of x. Well, we have 1 over cosine of inverse sine of x, which is going to be the same as 1 over square root of 1 minus x squared. And that is going to be, at least to me, a nicer looking formula. I don't know, Nathan, you tell me. Would you rather evaluate 1 over square root of 1 minus x squared, or would you rather evaluate 1 over cosine of inverse sine of x?
1 minus, or 1 over, yeah, the new one.
The new one? Why is that?
Easier.
Looks easier?
Yeah, it's not as many trig functions.
Yeah, there's not many trig functions. In fact, how many trig functions are showing up here? Jonah?
0.
Doesn't look like there's any trig functions, which is kind of weird. Because when you think about, like, if you just differentiate sine of x by itself, it has a derivative that's another trig function, cosine. When you differentiate inverse sine, you can either write it using 2 different trig functions, or 1 trig and 1 inverse trig function, or you can write it in a way that doesn't appear to use any trig functions at all. if you ask me, is kind of cool. It's going to have some interesting implications for us once we start talking about inverse trig integrals. But the main idea is we did some implicit differentiation to find a formula for the derivative of inverse sine that kind of uses cosine 1 over cosine of inverse sine of x. And then to simplify that out, we did a little bit of right triangle trigonometry, some SOHCAHTOA, to say, well, we want to know what cosine of inverse sine of x is. Well, that's the same as saying cosine of theta, if we just let theta be inverse sine of x. And then by doing a little bit of Pythagorean theorem manipulation here, SOHCAHTOA, we're able to find a much nicer looking formula for cosine of inverse sine of x that didn't rely on any trig expressions at all. Any questions or comments related to that? All right, I want to do the same thing now with inverse tangent. So let's say we start off with y equals inverse tangent of x. And we want to go through a similar sort of process in order to find the derivative of this function. Kate, any ideas how we would get started?
Tangent of y equals x.
Okay, rewrite it in terms using something we already know. Tangent of y, this is the same as saying that tangent of y is equal to x, along with y has to be between negative pi over 2 and pi over 2, but that's not going to be super important for us. Groovy. Where can we go from here?
Differentiate in respect to x.
Okay, so we're going to differentiate both sides of this with respect to x. I'll do that one. How do we differentiate tangent of y with respect to x? Using some good old-fashioned implicit differentiation. Phoebe, any ideas?
Well, if we know the derivative of like tangent, we can use that, like use the chain rule.
Do we know the derivative of tangent? What is it?
Secant squared?
Mm-hmm. Yeah. Derivative of tangent is secant squared, so we're going to get secant squared of y when we do that. And then Phoebe, you said you wanted to use the chain rule somehow? How'd you use the chain?
We're supposed to take then like the derivative of y with respect to x.
Ah, so then we'll have a times dy dx term that pops up. And that comes from using the chain rule on tangent of y, or doing implicit differentiation, we've also called it. Groovy. So we get secant squared y times dy dx is going to be equal to 1. So with that in mind, what would dy dx be equal to? Lauren? If secant squared y times dy dx is going to be equal to 1, what happens if we try and get dy dx by itself? Yeah, we're going to get 1 over secant squared y. What's the next one? Let me start that over. How can we rewrite this, Taylor, so it's instead of formula that's in terms of y, it's a formula in terms of x instead. Do we know how to write y as an expression in terms of x? No? What did we say up here that y should be equal to? Yeah, y is just inverse tangent of x. So when we say 1 over secant squared of y, that's the same as 1 over secant squared of inverse tangent of x. Which if we wanted to, we could write out as being cosine squared of inverse tangent of x, using the fact that secant is 1 over cosine, cosine should be equal to 1 over sequent. Sequent? Secant in a similar way. Mine's jumping ahead a few standards sequences. Cool. We get cosine squared of inverse tangent of x. Gosh, it would sure be nice if we could find another way to write this that doesn't have any trig functions somehow. So if we do that, I think we could do a similar trick to what we said over here. We want to find what cosine squared of tangent, inverse tangent of x is equal to. So we're going to draw the right triangle again. This time, Nora, any ideas on what a useful theta substitution might be?
The tangent of theta is equal to x over 1.
Okay, yeah, so define theta, in other words, to be inverse tangent of x, so that tangent of theta is equal to x. Sounds good. So if we do that, we can let theta be equal to inverse tangent of x. So that then tangent of theta would be equal to x, which is the same as x over 1. Nora, out of curiosity, why did you let theta be inverse tangent of x instead of inverse cosine or inverse sine or something else?
Because we want to solve for tangent.
Yeah, well, because we're trying to find cosine squared of this specific inverse trig function. So, in other words, we can find what cosine squared of theta is. So using the TOA part of SOHCAHTOA, we know that the length of the opposite side divided by the length of the adjacent side should be equal to x over 1. So we can even write that in. Beep, bop. Let's see. Caleb, how can we find what the remaining, if this side is length x, this side is length 1, how can we find what the length of the hypotenuse of this right triangle would have to be?
The Pythagorean theorem, so it'd be 1 squared plus x squared equals c squared.
Yeah, so we'll get 1 squared plus x squared equals c squared, which would imply c is equal to?
1 plus x.
Careful, you can't just take the square root of each piece separately.
The square root of 1 squared, or 1 plus x squared.
Yeah, it's going to be square root of this side, which is 1 plus x squared. Using that 1 squared. Which is not the same as square root of 1 plus square root of x squared. Just so everyone's on the same page. It's an easy mistake to make, but square roots don't break up nicely over sums, unfortunately. All right. Square root of 1 plus x squared. And now, if we want to find what is cosine squared of inverse tangent of x, we need to find cosine squared of inverse tangent of x, I think is just going to be the same as cosine squared of theta, using Norris substitution of theta equals inverse tangent of x, which is the same at using the ka part, see it in bird call this time, adjacent over hypotenuse quantity squared, since we're taking cosine squared and not just cosine. If we take adjacent over hypotenuse, Kate, what's that going to give us? You're doing it some other way over there, aren't you?
Well, I was just using the other method, but yeah, it would be 1 over 1 plus x squared.
Yeah, we're going to get the quantity 1 over square root of 1 plus x squared, quantity squared, which in the end is going to give us 1 squared over square root of 1 plus x squared squared, a lot of squares there, or 1 over 1 plus x squared. And thus, we can say that the derivative of inverse tangent of x would be equal to 1 over 1 plus x squared. Again, very similar process to what we just did. We do some implicit differentiation to start by finding dy dx as cosine squared of inverse tangent of x. And then we do some right triangle trigonometry with a sneaky substitution here in order to write that in a way that doesn't appear to use any trig functions at all. By the way, standard 5 quiz, which is going to be on Friday, just to be clear. These sort of questions would be I think would make for a good quiz question. Something like, hey, y equals inverse tangent of x. Prove that that derivative is 1 over 1 plus x squared, using this sort of approach. So, quick sum up before I let you go. We're not going to do this for all 6 trig functions. Just in the interest of time, they're all fairly similar. But it turns out, if we were to use this process, we would get the derivative of inverse sine of x is 1 over square root of 1 minus x squared, we found earlier. The derivative of inverse cosine of x is going to be the same thing, but negative. The derivative of inverse tangent of x, well, we just found that. That's 1 over x squared plus 1, or 1 plus x squared. And you all are getting restless. The other 3 are in the packet. But when we come back on Wednesday, we're going to finish off Standard 5 by talking about how can we use these sort of inverse trig derivatives to help us evaluate some integrals a little bit more nicely. So with that, hope you all have a good one. I'll see you all on Wednesday. See you later.